Welcome to Data Mining, Lecture 4, Part 1, Classification. This lecture is pretty long, so we divide this lecture into two parts, Part 1 and Part 2. What is classification? A classifier is trained by a given set of training data in which each object has a label and it belongs to a predefined class. And then the classifier is able to assign, after trained, an unlabeled object to one of the classes or indicate the unlabeled object doesn't belong to any of the existing classes. That's the definition of classification and how a classifier works in reality. There are numerous applications of classification. One application is for credit approval. Suppose a customer tries to apply for a credit card or tries to apply for a loan or mortgage. The customer will type in some basic data, such as the income, such as the gender, health situation, and some other background information. And then the classification program maintained by, for example, that credit card company would then classify that customer into one of the existing classes. Whether this customer is good, or whether this customer is, might have some problems in the future, and so on. And then make decisions regarding whether, the credit card should be granted or not, or whether the credit should be approved or not. Okay? So based on the data entered by this potential customer, the classification program is able to classify this customer into one of the existing classes. For example, one class might contain all the customers that are the best customers that have the best credit history, and one class might contain customers that have poor credit history, and normally we should not give them mortgage, and so on. Okay? That's one application of classification. Target marketing is another application. Disease treatment. I have already explained to you how bioinformatics companies or drug companies discover drugs by using the classification algorithms. What they do is they classify existing proteins into several families or classes or categories. For example, family 1, family 2, family 3, family 4, and so on. And they know very clearly about the characteristics of proteins belonging to the existing family. Suppose these proteins are extracted from diseases. They know what kind of medicines or drugs should be used to treat the diseases relevant to a particular family. Now, tomorrow, suppose you have a new disease that is unknown, and the scientists extract proteins from that disease, and then they use a classification program they have to try to classify that protein into one of the existing classes. Suppose the classification algorithm can tell us that that unknown protein should belong to family 122. For that case, we can use drugs for family 122 to try to treat that unknown disease to see whether that drug can be effective or not. Okay, that's a simple scenario, but that shows you why classifications are important in practice. And the classification using the machine learning terminology is known as supervised learning because the classifier is supervised and is trained by some training data first. I'm going to describe to you specifically how a particular classification algorithm is trained by training data in the next few transparencies. On the other hand, you also have clustering, which is to divide a set of data into groups or teams or families. And that clustering is known as unsupervised learning because clustering doesn't go through the training phase. And we will see different algorithms for clustering during the clustering lecture. So in this lecture, I'm going to talk about a particular classification algorithm known as decision tree induction algorithm. And after I go through this algorithm and example in detail, you will be able to learn how a classifier is trained by training data, and how, after that classifier is trained, how that classifier can be used to classify unlabeled or future unknown objects. In a decision tree, internal nodes represent a test on an attribute. So in this example, we talk about attribute-oriented data, meaning that each training example is just like a tuple or record in a relational database in which there are several attributes. Okay? And then at each level of this decision tree, you try to test on a particular attribute that you choose, and based on that attribute, you have different outcomes. So branches represent an outcome of the test. And the leaf nodes of the decision tree represent class labels. Whether that leaf node should belong to class 1 or class 2 or class 3 and so on. You have several existing predefined classes when you do the classification. Okay, in the previous protein example, you have family 1, family 2, family 3, and so on. These are existing classes or families. Now, how you come up with these classes? Well, in biology, they can be obtained by previous lab experiments and so on. Okay, in practice, this data can be obtained by doing the survey and so on. Okay, we will see one particular example in the next few transparencies. The decision tree algorithm is good for categorical attributes with non-continuous values. By categorical attributes, we mean attributes that can be categorized. For example, gender, you have female, you have male. Okay? The values are not continuous. A typical example for continuous values is real numbers. You have 3.5, 3.51, 3.511, 3.51111, and so on. These values are continuous. Non-continuous values refer to, for example, male, female. Or, for example, rich, poor. These are non-continuous values. And the particular algorithm we are going to introduce or describe is ID3 and its modification C4.5. ID3 and C4.5 are most famous decision tree algorithms, are the most famous decision tree algorithms that have been published in the machine learning field and then later on borrowed by data mining people. And these algorithms are very powerful and very useful, as you will see in the next few transparencies. So these are general ideas and the terminology. So how to generate a decision tree? And after decision tree is generated, how you are going to use that decision tree to generate classification rules. So these are the questions that I'm going to answer in the next few transparencies. So this is a typical training data set example in which you have several training examples or training tuples or training records. In each training record, you have a bunch of attributes. Okay? So the question here is that we want to know whether a customer would like to change to new AT&T calling plan. Okay? And this is a binary classification problem in the sense that you have only two classes. Yes, I want to change it to new AT&T calling plan. No, I don't want to change to AT&T calling plan. So yes, no classification, which is also known as binary classification. You have only two classes, either yes class or no class, and you have no other choices. Is that clear about this class labels? So yes class could be referred to as positive class, and the no class can be referred to as the negative class. And you have a bunch of training examples. As I said earlier, these training examples could be obtained from the survey or could be obtained from the existing data. You can just organize them and you find this information and you use this as the training data. Training data are very simple. When you train a small kid, you tell them that this is a television, this is a bottle of water, and so on. You have this knowledge, so you can train that small kid by telling them with these different shapes, they refer to different objects. And tomorrow, when you see a different shape, when you see this, you ask the kid what it is. And the kid has been trained already, so he or she is able to tell you that this looks like a computer because it is the shape is a rectangle similar to this shape, or something like that. But he or she will not tell you this is a bottle of water because the bottle of water looks like this, and they look very different. Okay, so this is to train a kid using the shape knowledge. But then you can tell the kid more knowledge. This is how you train a classify. Similarly here, we have this knowledge here. This data is at hand. Okay, this is given. So this is given data to your algorithm, to the ID3 algorithm or C4.5 algorithm. You have these training examples. And you know that if the phone usage is less than $75 or 75 minutes, and the income source for that family is only one person is making money, the living place is in the city, the current carrier for that family is MCI for that case, then that customer will change to new AT&T calling plan. You know this data. This is given. You obtain the data by, for example, making a survey or by looking into the current data in the database. If the phone usage is between $75 and $150 or minutes, and suppose there are two persons who have income in this family, and this family is living in town, and the current carrier is MCI, yes, that family would like to change to new AT&T calling plan. So these are classes. This tuple or training example belongs to the positive class. This belongs to the positive class as well. Now, if this family has less than 75% phone usage, only one person is making money, and the family is living in city, and the current carrier is Spring, no, that family will not change to AT&T calling plan. So these class labels must be given. Okay, you should tell the classifier clearly whether this training tuple or training example belongs to the positive class or belongs to the negative class. Is that clear to you about this training example? So these training examples or training records are given to your algorithm, and your algorithm will output a decision tree like this. So the previous transparency gives you the input data, and this transparency gives you the output of your algorithm. So the decision tree says the following. You can look at any particular branch. For example, I look at this branch. If the phone usage is less than 75, and if the current carrier is MCI, then yes, that particular family should belong to the positive class. That is, that family will change to new AT&T calling plan based on your training example, based on your training data set. If the phone usage is between 75 and 150, and suppose the income source for that family is 1, and that family lives in town, then that family will change to new AT&T calling plan. If the phone usage is between 75 and 150, and the income source is 2, there are 2 persons making money in that family, then yes, that family will change to new AT&T calling plan. If the phone usage is less than 75, and if the current carrier is AT&T, then no, that family will not to change new AT&T calling plan. They will still use the older plan. If the phone usage is between 75 and 150, and the income source is 1, and that family lives in city, then no, that family will not change to new AT&T calling plan. So, given the previous training database, we are able to generate this decision tree that reflects what happens in those training examples. But the question is how you are going to generate this tree based on the previous training tuples. So from the previous training database to this tree structure, the story is non-trivial. And that's the whole beauty or contribution of the ID3 algorithm or C4.5 algorithm. Okay? Quinlan from the University of Melbourne, I think, in Australia, is one of the first who discovers this algorithm, which accepts training data and then prints out decision tree. Prints out decision tree like this. And all the decisions here are consistent with what are said in the training examples. You can verify this by checking the training example. You see that everything here indicated in this decision tree is consistent with what you say in your training database. Any question about the whole story? So I'm going to teach you, given a training database, how to generate a decision tree. The algorithm works as follows. The algorithm is known as ID3 or C4.5 algorithm, which are the most famous decision tree induction algorithms in the field. Now, of course, there are a lot of modifications and improvements over these original algorithms, in the recent papers. And we are going to talk about one particular algorithm at the end of the semester, which is improvement of this original algorithm. But those are only improvements. This is the original, and you see how different they are. Original things are the most difficult things in science. Okay, so the number one is always the most difficult. Subsequent things are just the improvements or modifications or extensions of the original algorithm. The algorithm works as follows. At each level of the tree, we select an attribute to branch on, and we always select the attribute with the highest information gain. So the whole story is to teach you how to calculate this measure, information gain. Okay? And in our particular example, we have only 2 classes. Positive class, meaning that members in that class will change to a new AT&T calling plan. And the negative class, which contain all the members who are not going to change to AT&T calling plan. So you have a positive class and a negative class. And suppose in the positive class, you have P training examples. How do you get a P? You can look at the whole training database once, and you just count how many positive training examples in that database, and that gives you the P. In our example, positive training examples are those training examples that have yes for changing the calling plan. Okay, so the yes is indicated in the last column in that training table. Negative training examples are those training examples that have no in the last column in the training table. This means that these training examples will not change to new AT&T calling plan. So you can always count the training examples, and you can always get this lowercase letter p and the lowercase letter n by looking at your given training examples. And then you use the number p and number n, plug them into this formula you can calculate IPN based on the formula. Okay, the formula is invented by Quinlan and the colleagues. So basically, this is a magic formula. Okay, you just calculate P divided by P plus N log 2 and so on. In our previous training example regarding whether you want to change to AT&T, new AT&T coding plane, there are 9 positive training examples, meaning that there are 9 training records that indicate yes. And there are 6 negative training examples, meaning that there are 6 training records that indicate no. They don't want to change to new AT&T coding plan. So 9 plus 6 is 15. So the denominator is 15. And you can just, substitute those numbers into this formula, and you can get IPN. Any questions so far? Then you look at each attribute in turn. In my previous training database example, how many attributes we have for each training record? You have phone usage. You have living place, city or town. You have current carrier, AT&T, Sprint, MCI. You have income source, 1 income or 2 incomes, and so on. So you have attributes, phone usage, so income source, current carrier, and what's that? Yeah, there's a you have a bunch of attributes. Then you look at each attribute in turn. For example, suppose I look at phone usage. I look at that particular attribute, phone usage. Then I can divide the training database or the training set into 3 subsets, S1, S2, S3. S1 contains those training examples in that training database whose phone usage is less than 75. S2 contains those training examples in the given training database in which the phone usage is between 75 and 150. S3 contains those training records or training examples in which the phone usage is greater than 150. All right? So look at the whole training database or training set. You have a lot of training examples. In my previous example, we have 15 training examples. Right? Now you look at a particular attribute, says phone usage. Phone usage. You have 3 possible choices. Phone usage is less than 75. Phone usage is between 75 and 150. Phone usage is greater than 150. Okay? So you can divide these training examples into 3 classes. In the first, or into 3 sets. The first set, S1, contains those training examples whose phone usage is less than 75. The second set, S2, contains those training examples, those given training examples in which phone usage is between 75 and 150. Set S3 contains those training records or training examples in which the phone usage is greater than 150. So you can just, based on the phone usage, you can divide the whole training examples into 3 sets, S1, S2, and S3. Totally, you have 15 tuples or 15 given training examples. So you can divide them into 3 sets, S1, S2, S3. In each set, for example, in S1, you can look at these tuples, and you know how many tuples are in the positive class. Look at whether they are yes or no, and how many are in the negative class, and so on. Is that clear so far about the data? Now, you look at for example, S1 for the phone usage attribute. And then you know how many positive examples in that S1 and how many negative examples in that S1. So you get a lowercase letter P1 and a lowercase letter N1. Then we can calculate the entropy or the expected information needed to classify objects in all subtrees S1 based on the entropy of that particular phone usage attribute. So the entropy of phone usage attribute is equal to this number. P, you know, the numerator is pi plus ni from 1 to 3 for the phone usage attribute, and the denominator is p plus n, where p is the total number of positive training examples in your training database. In our case, it's 9. And n is the total number of negative examples in our training example. So you get the n, which is 6, okay? And then you can calculate IPI NI based on the previous formula IPM by substituting PI NI to P and N in the previous formula. You can calculate the formula easily. Because now you have PI NI, you also have P and N, and I have already explained to you the definition of the P and N. The number P here represents the total number of positive training examples in your training database. So you can look at these training examples. You look at how many years you have. You have 9 in our previous example. So P is 9. And the lowercase letter n represents the number of negative training examples in your training database. The training database is given. So you just look at the database. You can count, and you can know how many negative training examples in your database. In our previous example, the lowercase letter n is 6. Okay? Then, what is PINI here? For example, suppose attribute A here is phone usage. Then, for the phone, you look at that particular attribute, look at the values in the attribute, phone usage. You have 3 possible choices. Phone usage less than 75, phone usage between 75 and 150, and the phone usage greater than 150, right? So you can divide these tuples into 3 sets, S1, S2, S3, where S1 contains those training tuples or training examples whose phone usage is less than 75. And S2 contains those training tuples whose phone usage is between 75 and 150. And S3 contains those training tuples or training examples whose phone usage is greater than 150. You can just look at the data there. You can do this, you can do this organization. Now for the S1, the S1 contains all the training examples whose phone usage is less than 75, right? So you look at those tuples, then you can see how many belong to positive class and how many belong to the negative class by looking at their yes/no column. So you get a lowercase letter P1 and lowercase letter N1. P1 represents the number of positive training examples in a set S1 containing tuples with the phone usage less than 75. And N1 represents the number of negative examples in that set S1. You can just look at the data. You can easily calculate these parameter values P, N, P1, N1, P2, N2, P3, N3, and so on. Question? Louder, please.
How do you determine how many we could have? In this case, in this case that we have that we use the amount of usage in terms of like less than 75 or 75 to 150 or more than 150. So it becomes 3 cases here. My question is how do we consider in terms of how do you find that V?
Okay, let me try to repeat your question. The question raised by the student is that in general, how do we calculate this V? How do we know how many sets we have for a particular attribute? That data is in the given training database. You look at the training database. Let us, for example, look at the other attribute, income source. How many V's we have for the income source? You have only 2 choices, 1 and 2. So everything is from the training database. We do not invent anything. We just look at the database and then use the data in the database to determine the number V.
I understand that this is the number in case of like as you say the source of income it becomes just 1 or 2 or 3. But
that's a good question. So the student raised the question that in general, if the values are continuous, how do you know how many V's you have? But I have to remind you once again that this algorithm, particularly known as ID3 or C4.5 algorithm, is only for categorical attributes with non-continuous values. That's all, right? So this algorithm works best for relational data where you have attributes and you have values. For other scientific disciplines where you also do classification, this algorithm doesn't work for those applications. For each application, you come up with different algorithms suitable for your application. This ID3 algorithm is only suitable for categorical attributes with non-continuous values. That's the limitation of this algorithm. We do not have a generic or universal algorithm that works for every domain or for every application, to do classification. That's basically the situation. So the information gain for the particular attribute, for example, phone usage, is equal to IPN for that attribute minus entropy for that attribute. IPN actually is just a generic number, right? You look at the previous formula. IPN is equal to some P plus N divided, and then you take the log and so on. And this Pn are all obtained from the training data. You look at the data, you have 9 positive examples, so the P is 9. You have 6 negative training examples, so N is 6. You just plug these numbers into the formula without looking at each attribute particularly. So this IPN is nothing to do with a particular attribute. EA, on the other hand, is an entropy for a particular attribute A, so this is obtained for that particular attribute. For example, if you look at the phone usage, then you can divide the tuples, the training tuples, into 3 sets, S1, S2, S3, because you have 3 possible choices. Phone usage less than 75, phone usage between 75 and 150, and the phone usage greater than 150. If you look at the income source, you have only 2 choices, so you can only divide the tuples into 2 sets, S1 and S2. S1 contains training examples with only 1 income source. S2 contains training examples with 2 income sources. If you look at the current carrier, you might have 3 choices. The current carrier could be Sprint, the current carrier could be MCI, the current carrier will be AT&T. These data are all from the training database which is given. Okay? And based on the data, you can, for example, if you look at the current carrier, you can divide the tuples into 3 sets, S1, S2, S3. S1 contains all the training examples in which the current carrier is MCI. S2 contains all the training examples in which the current carrier is AT&T. S3 contains all the training examples in which the current carrier is Sprint. And for each SI, for example, for S1, then you can look at how many positive training examples in S1. That is, how many examples have yes for changing the coding plane. How many are negative examples in the S1. You can get all these numbers by looking at the training database. All the numbers are there, okay? And then you plug those numbers into the formula. You can get the information gain. Okay, so we have 2 classes. The positive class that indicates that the change plane is yes. Negative class that indicates that change plane is no. And then we can compute the expected information IPN, in which we have 9 positive training examples and 6 negative training examples, and we can plug them into this formula IPN, and we get a 0.971. When IPN is, sometimes we want to calculate IPINI as well, PINI for particular attribute. For that case, you just calculate PINI and you plug those PINI numbers into the formula, you can get the appropriate number. Any question about these calculations? So you get a 0.971 for IPN, okay? That number is there for every attribute. So now, as I said earlier, at each level, the algorithm looks at attributes and then choose the attribute with the highest information gain and branch on that particular attribute. Use that attribute as a test case and then do the branching. Okay? So which attribute we should choose at each level? We choose the attribute to branch on with the highest information gain. And I already explained to you how to calculate information gain for each attribute, right? For example, for the phone usage, so you can divide the phone usage into 3 sets, less than 75, between 75 and 150, greater than 155. And then for this set, you can calculate how many positive training data in that set. You have one positive training example in that set, and you have 5 training examples that indicate no in that set. So Ni is 5 for this training set. And therefore, you can plug these numbers into IPM formula by replacing PM by this PINI, and you can get the number 0.65 for that number. So you put it there. Similarly, for the second set, S2, in which we have all the training examples whose phone usage is between 75 and 150, you can once again look at the training database. You can calculate how many positive training examples in the set S2 and how many negative training examples in the set S2, and you can plug these numbers into IPM formula. You can get an IPNI, which is 0.65 for this S2. Similarly, you can calculate S3. You can get these numbers. And then the entropy for the phone usage is equal to this formula, which is obtained from the previous transparency. Okay? 6 divided by 15 multiplied by IP1 N1, which is 0.65 here, so you plug 6.65 into this number, plus 6 divided by 15, I51 and I30, and you get this number from this table. You can plug into this formula, and finally you get this number 0.52. All these numbers are obtained from the training database. So you get the number 0.52. The entropy for the phone usage is 0.52. The information gain for the phone usage is equal to IPN, which is 0.971 that we have calculated in the previous transparency, minus the entropy of the phone usage, which is 0.52. So you get the information gain for this phone usage attribute, which is 0.451. So always keep in mind that during the final exam, you should bring your calculator to do the calculation. In the last semester, 2 students forgot their calculator, and there was no way for them to do this detailed calculation during the decision tree class construction. All right, so it gave them a lot of hard time during the exam. This needs a lot of calculations, so the calculator is always there, should always be with you during the exam. So after you calculate the information gain for the phone usage, then we look at the information gain for the second attribute, income source. For the income source, I can divide the training data into 2 sets, S1 and S2. S1 contains all the training examples in which the income source is 1. And S2 contains all the training examples in which the income source is 2. And you can get this data from the training database. For the S1, you can count how many positive training examples. That is, how many training examples have yes, okay, for changing the coding plane. And you can count how many negative examples in that S1. So in our case, you have 3 for P1 and 3 for N1. And you can plug these numbers into the IPM formula. You can get IP1 N1, which is 1 in our case. For S2, you do similar calculations and a similar counting on the original training database. So you have 7 positive training examples in S2. You have 2 negative training examples in the S2, where S2 contains all the training tuples whose income source is 2. All right? And you plug these numbers into IPM formula, you get this number 0.764. And then you calculate the entropy for the income source. By plugging these numbers into the formula, you get a 0.858. And then information gain for income source is equal to IPA, which we have calculated in the previous transparency, which is 0.971. This number is nothing to do with any particular attribute. Okay, it's there. Entropy I source, that's relevant to this particular attribute, income source, and that number is 0.858. 0.971 minus 0.858, that gives you the number 0.113. Okay, that's the information gain for income source. And then we do the similar calculation for living place. You live in a city or you live in a town. You calculate the information gain for living source using the similar calculation, and you get a 0.035. and you do the similar calculation of information gain for current carrier. Okay, and the information gain of this attribute current carrier is 0.063. Among all the 4 attributes, phone usage, income source, living place, and the current carrier, which attribute has the highest information gain, where the information gain for each attribute is calculated in a previous transparency? Which attribute has the highest information gain? The phone usage has the highest information gain. Therefore, we decide to branch on the phone usage at this level, actually at the top level. All right? So we partition the training data set by phone usage. So, and there are 3 choices. Either the phone usage is less than $75, or the phone usage is between 75 and 150, or the phone usage is greater than 150. Okay? Now, for the whole original given training data set or training database, you have 15 tuples in total. 9 tuples are positive tuples, positive training tuples, meaning that they will change to new plane. 6 tuples are negative training tuples, meaning that they will not change to new AT&T coding plane. And these labels or these class labels, like a positive, negative, are given. Okay, you have to give these class labels explicitly to the algorithm. You tell the algorithm, if this tuple satisfies this phone usage income information, then that tuple belongs to the positive class, and so on. Or that tuple belongs to the negative class. You have to tell the algorithm whether that tuple belongs to the positive class or that tuple belongs to the negative class. You have to tell the algorithm explicitly whether that tuple belongs to yes class or belongs to the no class. Okay, that's the fundamental rule we have to observe when we do the classification. Okay, algorithm has to be trained first. Now, look at the phone usage. When the choice is less than 75, you go back to the original training database, and you can see that for this choice, you have 1, 2, 3, 4, 5, 6. You have 6 training tuples that satisfy this value out of 15 tuples. These 6 tuples all have the phone usage less than 75. And we refer to this as a reduced training database. And subsequently, along this branch, we are going to work on this reduced training database only. Let us look at the reduced training database. Every tuple has a phone usage less than 75. That's for sure right now. Now, you have a bunch of tuples that say no. In fact, you have 1, 2, 3, 4, 5. 5 tuples that belong to negative class, and 1 tuple that belongs to the positive class. And for each tuple, if you look at the original data, you still have the income source, city information, and the current carrier information. This information might differ among these tuples. The only thing that is shared by all the tuples is that all of them have the phone usage less than 75. Is that clear to you? And then, so that's the reduced training database along this branch, less than 75 branch. Similarly, we can look at the regional training database and pick up those tuples that have the phone usage range between 75 and 150 and put them in this reduced training database. Now, again, if you look at the tuples here, they have different source income, different living places, different carrier. So all the tuples share the same thing. Namely, they all have the phone usage between 75 and 150. And some of them belong to the yes class and one belongs to the no class. Okay? This class information must be clearly given to the algorithm. So they are here. Similarly, you have this data or this reduced training database for this branch. All the tuples here have the phone usage greater than 150. They might have different income source, they might have different living place, they might have different current carriers, and they might have In general, they might have different classes and so on. All right. So if you count this, the total number is 15, and you divide them into 3 sets based on the 3 different outcomes for the phone usage. Now we are going to focus on this particular reduced training database, and we are going to work on this reduced training database. Once again, based on that reduced smaller training database, we want to pick up one attribute on which we can branch. Now, once again, we repeat all the calculations about information gain for each attribute, for each remaining attribute. Phone usage has been chosen already. So the only 3 remaining attributes we consider from now on are income source, living place, and the current carrier. So let me calculate the information gain for phone usage less than 75 for the income source attribute. Now, you have to keep in mind right now that the total number of positive examples and the total number of negative examples have been changed, because right now we are working on the reduced training database rather than the regional training database. So the P right now is 1 and the N right now is 5. We have only 6 tuples in the reduced training database. One of them is a positive example and 5 of them are negative examples. So you plug this number 15 into your formula IPN, you can get this number. So this IPN is different from the previous IPN, which is 0.971 something. This IPN is with respect to your reduced training database, that is your training database with respect to the phone usage less than 75. Any questions so far? And then, right, you now have only 3 remaining attributes that you can consider: income source, living place, and the current carrier. So let me look at the income source. I have, once again, based on that reduced training database in which I have only 6 tuples, I can divide them into S1 and S2. S1 contains all the tuples with 1 income, and S2 contains all the tuples with 2 incomes. Okay? And then again, by looking at that reduced training database, I can calculate how many positive training examples in S1 and how many negative training examples in S1. Right now, you only look at that reduced small training database with respect to the phone usage less than 75. So the number here, P1, N1, will be normally smaller than the P1, N1 in the previous iteration when you consider all the training data in the training database. All right? So you do the similar calculations. You can calculate the entropy of the income source with respect to the phone usage less than 75, and you can calculate the gain for this income source. And this gain of income source will be different from the gain of the income source in the previous iteration where you look at the whole training data in a given training database. Right now, you only look at the reduced training database, that is with respect to this phone usage less than 75. Is that clear to you about the whole story? So this algorithm is very simple but beautiful. Okay? So the gain of the income source is 0.109. You do the similar calculation for the information gain for living place with respect to the phone usage less 75. You can calculate the information gain. You can calculate the information gain for the current carrier with respect to the phone usage is 7.775, and with respect to that reduced training data set. All right? So now, the information gain for the three remaining attributes, income source, living place, and the current carrier, is shown here. Which attribute has the highest information gain? Louder, please. Current carrier has the highest information gain. Therefore, we choose this attribute to branch on in constructing the decision tree. So we look at the current carrier. There are 3 possible choices. The current carrier could be MCI. For this current carrier, the class is yes, based on my training data. When the current carrier is Sprint, then the class is always no. When the current carrier is AT&T, the class is always no, based on my training data here. So I understand that I have only 3 choices, And based on each choice, I can tell you whether that goes to yes or that goes to no. And after I reach this level, I'm done. I don't need to consider the other two attributes, in place and income source, because all the tuples can be categorized into one of the classes here. I'm done. I have only 6 tuples left here, and they either go to yes if they choose MCI, or they go to no if they choose Spring or AT&T, and I'm done. I don't classify any further. Okay, so I reach the leaves, and I know that all the tuples along this branch can be classified in the right way. They either go to yes or no, and no tuple will be unclassified along this branch. So I'm done. Then I look at the second branch. The second branch concerning phone usage between 75 and 150. And this is the reduced training data I have at hand. So in general, you have to calculate the information gain for each attribute again, and you decide which attribute you should branch on. All right? And then I also look at the reduced training data along the branch greater than 150. Now, for this particular example, it turns out that every tuple in this training data, in this reduced training data, belongs to the positive class. So I know that I do not need to do further classification because every tuple actually belongs to the yes class. So if I go to this branch, then the only class I can reach is yes. So I put a yes here. I'm done along this branch. So the only branch I haven't finished yet is the middle branch. Okay? Because I still have different choices. All right? So for that rightmost branch, I put a yes there, meaning that every tuple that have phone usage greater than 150 will be positive tuple and will change to new AT&T coding plane. No doubt for them. So that's yes, for sure. All of them belong to the positive class, the yes class. Okay? So now, the only thing I should focus on is this middle branch. So this is the branch I'm going to focus on. Now, once again, I have to look at the 3 remaining attributes, namely income source, living place, and the current carrier, and see which attribute has the highest information gain. And I'm going to choose that attribute to branch on. All right? So I do the similar calculations. With respect to that smaller, reduced training database along the second branch. So these are the information gains for the 3 remaining attributes in the middle branch of the decision tree. Which attribute has the highest information gain in this particular example? Income source turns out to have the highest information gain. So I decide to select income source. And then based on the income source, I look at the training tuples in the reduced training data set. If the income source is 2, yes. If the income source is 2, yes. If the income source is 2, yes, yes. So if the income source is 2, I know that based on the training data, the only answer is yes. All the tuples should go to the yes class. They all belong to the positive class. For the income source 1, this is no. For the income source 1, this is yes. So the income source 1 is still uncertain. But for the income source 2, it's for sure in the positive class. So for the income source 2, I have this further reduced training data in which every tuple belongs to the positive class. For the income source 1, the choices are more diverse. Okay? So for this class, I put a yes. Now for the income source 1, you have 2 choices, right, in the previous slide. But then when I look at the city, when I look at the living place, if it's city, the class is no. If the city is town, the living place town, the class is yes. So then I decide to branch on the living place. So I end up with living place, city, no, town, yes, I'm done. Now in general, of course, you have to do the information gain calculation on the living place and current carrier based on the further reduced training database here. But for this particular simple example, I know that I have only 2 tuples left, and if the living place is city, then that tuple belongs to the no class. If the living place is town, that tuple belongs to the yes class. And both tuples actually choose the MCI, and so MCI becomes insignificant. We have to look at the living place information to make decisions. Okay. In general, once again, you just calculate the information gain once again for each remaining attribute, and you can decide which attribute you should branch on. You pick up the attribute which has the highest information gain to branch on. In our particular example, it's surely that the living place has the highest information gain between living place and the current carrier. The current carrier tells you nothing because the current carrier both have MCI, so it cannot tell you anything. The living place tells you that if it's city, then that tuple belongs to the negative class. If it's town, that tuple belongs to the yes class. Okay? So far, the tree has been constructed entirely, and every tuple belongs to one particular class along with branches in the tree. And that's all. Okay? Now, after you have this tree, you can generate decision rules or classification rules from this tree. For example, if a tuple has a phone usage less than 75 and the current carrier is MCI, then you know that that tuple should be in a positive class. That's one rule. So tomorrow, if you have a new tuple submitted, and that you look at that tuple has a phone usage information, current carrier information, income source information, living place information, and so on, right? One tuple. The only information missing for that tuple is the class information. We don't know which class that tuple should belong to. So we use this decision tree to classify that unknown tuple. How to classify? You look at the phone usage of that particular tuple. If the phone usage of that unknown tuple, unlabeled tuple, is 75, it's for example 85. So you know that you should follow the middle branch because the middle branch covers all the cases whose phone usage is between 75 and 150. So you look at that unknown tuple. That unknown tuple has the phone usage information, has the current carrier information, has the income information, has the living place information. The class information is absent, and the classifier will tell you which class that unlabeled tuple will belong to. Now, how to do the classification? You look at that tuple, right, and look at the decision tree. The top level is to look at the phone usage attribute. So I look at the phone usage of that unlabeled tuple. If the phone usage of that unlabeled tuple is 90, for example, then I look at the decision tree. Okay, 90 should come to the second branch because the second branch covers everything, all the phone usage information between 75 and 150. You have 90 there, so I should follow the second branch. Okay? Then the second branch tells us that I should look at the income source of that unlabeled tuple. So I look at the income source of that unlabeled tuple. If the income source is 2, for example, then following this decision tree, I know that that tuple should belong to the positive class, meaning that that tuple is classified into the class in which that family should change it to the new AT&T coding plan. If the income source for that unlabeled tuple is 1, then I look at the living place of that tuple. Is it in a city or is it in a town? If it's in a city, then I know that that tuple should belong to the negative class, meaning that that tuple, that family, or that customer will not change to new AT&T coding plan. So by looking at data in that unlabeled tuple, and by looking at the decisions in this decision tree, I'm able to classify that unlabeled tuple to either yes class or no class. By the way, this is for binary classification only, meaning that you have only two classes, either yes or no, positive or negative. In the next week, we are going to talk about other type of classifications where you have multiple classes, class 1, class 2, class 3, class 4, and so on, rather than only positive and negative classes. So that shows us how to generate classification rules from the constructed decision tree. You start from the root. If the phone usage is less than 75 and the carrier is MCI, then the change plan should be yes. You follow that branch. You know, when you reach the lead, that tells you whether that's a yes or no. If the phone usage is less than 75 and the carrier is Spring, then the change plan is no, and so on and so on. All the rules are generated by traversing this decision tree along each branch, and then you can find all these classification rules from that decision tree. Okay? And then after you have these classification rules, for any given unlabeled tuple, which contains phone usage information, carrier information, living place information, and income information, you are able to tell the decision maker whether that customer or that tuple or that family will change to a new AT&T plan or will not change to a new AT&T plan. Now, if you look at the whole story, you see that these decisions are actually constructed based on the previously given training data or the 15 training examples. So all the knowledge comes from the previously given 15 training examples. If the training examples are biased, then the decision rules will be incorrect. So for any classification algorithm, such as decision tree algorithm, such as neural network algorithm, the training data becomes important. The training data must be comprehensive enough. The training data should not be biased. If the training data are wrong, the decision rules will all be wrong, because the decision rules are generated based on your training data. Also, you should have sufficient numbers of training data or sufficient amount of training data. If your training data is too few, you cannot get good decision rules or classification rules. Okay, so these are heuristics for us to choose the training data. Once the training data is given, nothing can be changed. The decision tree will be just calculated or constructed based on this training data. And once the decision tree is constructed, then we use the decision tree to predict future situations, to classify future records or tuples. That ends Lecture 2, Part 1, classification.